let's suppose that we have a compound X. We don't know what X is, but we want to find out. So this is a mystery to us. How do we find out what this is? Well, we could do a series of reactions and try and figure out based on what we see what it is, or we could look at its measurements and try and cross-reference with a big textbook to see what it is, but that's pretty time-consuming and boring. So there's a much easier way that we can do this, and it's called spectroscopy. And the specific form of spectroscopy that we're going to be looking at today is mass spectroscopy. So using the Mass Spectrometer. Now, the Mass Spectrometer, as its name suggests, uses the mass of a compound to work out what it is. But how does it do this? Well, it uses 4 main stages and a principle that we'll look into now. So, first of all, before explaining any of the chemistry, let's think about what would happen if I have a giant fan. Let me just draw the fan in grey. I hope you can see this right with the colour. Let's draw a big fan. Its blades. I never said I was an artist. So we have a fan, and this is blowing air over here. Now, we have a target on the other side of the wall. And let's draw some blue on there to make it appealing. So we have a tennis ball, and we want to throw this tennis ball at the target. Now, if we throw it hard enough, it will just go and hit the target, providing we have good enough aim. But then if we do the same with a ping pong ball, that's a bit big for a ping pong ball, but just assume it's a big ping pong ball, and we throw that at the target, we'll see that it'll get blown away. Why is that? Well, the tennis ball is going to have higher mass. So this has a higher mass than this ping pong ball, which has a really low mass, which is why it's a ping pong ball. So, using this concept of things having high mass going through something trying to push away from it, and things with low mass being deflected, we can try and get away from molecules to be manipulated based on how much they weigh. So, how about, instead of using a giant fan to throw our molecules at, we use magnets? But, as we know, magnets only repel charged things. So, first of all, if we have our molecule X, we're going to need to ionize it. And an ion is just a charged particle. So, if we give, that's just to show that it's in the gaseous state. So if we give this particle an electron, then it will become X minus, still a gas. And then, maybe with this, we could use a magnet to try and blow it out the way like we did with a ping pong ball. And with the added benefit of we're able to change how strong the magnet is if it's an electromagnet. So, if we ionize it, then we're going to need to throw it as we did with this ping pong ball and this tennis ball. So if we throw it down a tube with a bend in the middle and a magnet here, so this is my magnet, then this charged particle is going to get deflected by the magnet. But then if we have different particles of X, let's say a heavier particle like we have with this tennis ball, the force that is strong enough to blow away this molecule, as it was with the ping pong ball, will not blow away this heavier molecule. So this heavier molecule will crash, but this light molecule, X, won't. So with this concept, we can perform mass spectronomy. And the machine that performs it, I have handily prepared earlier. This is a mass spectrometer. So, as you can see, I've coloured various parts of it. 4 of them in fact, because there are 4 stages that you need to know. This red bit is where the ionisation occurs. And then this green bit is where the molecules are accelerated. This is the acceleration. That is the bit where they get thrown. This tube in the light blue, as I indicated with the magnet, is where the deflection occurs. So the molecule gets blown out of the path if it's charged and if it's light enough. And then this purple box is where the detection occurs. So these 4 stages you need to know for exams. And that's why I've highlighted them. But let's look more in detail about this. So, ionisation. How do we ionize something? Well, if we have a metal coil here and apply electricity through it, so eventually it gets really hot and starts luminescing like a light bulb, what's happening is that electrons are being thrown out. So this thing is throwing out electrons. And if we happen to have a molecule in the way of this, with its electrons orbiting the molecule, if we knock one of those electrons off of it, then we will charge the particle. So if we get our compound X and then knock an electron off, so we give it an electron, but instead of charging it negatively, it knocks off another electron, we will form, sorry, wrong thing, I was going to put a plus, let's get rid of that, we will form a positively charged ion, and we will have 2 electrons remaining, because we've thrown 1 electron at it, and then we have knocked an electron off. So now this only has 2 electrons, unlike the 3 it had before, and this electron and this electron have been knocked off. So this one gets knocked off, and this one goes away. So now we have 2 electrons floated off. So that's how we ionize things. Now let's look at the acceleration. If I just rub out this stuff here. The acceleration is done by having our charged molecules, which I'll again represent with this, which now have a positive charge. We have these gates, circular gates with slits in them. If this plate is negatively charged, then the positive ion is going to be drawn towards it. And then this slit here ensures that particles going towards it fast enough to go through this slit are in a finely focused and extremely fast beam. So what we've essentially done up to this point is we've taken a molecule, we've ionized it, and then we've accelerated it to extreme speeds in a very narrow line. So if you imagine the tube where you've ionized it, the ionization center, and then it's coming out into the acceleration chamber. This is the ionization. This is acceleration. When we accelerate it to these 2 points, let's say, these green lines represent these gates. So when we first accelerate it, we're going to have a bunch of particles here that all move. Let me use a different color for this, make it a bit clearer. That all move the same direction towards these negatively charged plates here. But seeing as there is only a slit here, only the ones travelling directly here get through. And then we're going to have a few more spread around like this, out of all of these, and then only the ones going through this one are going through. So we've focused down the beam to a point where we had lots and lots moving all at the same time to a finely focused beam to an even finer focused beam. So we have condensed down that beam into one almost single beam of ions. But you should be thinking there's a problem with this. If this occurred in natural space, we're going to have molecules floating around. That's how we breathe. That's just the air. So in order for this to happen, and not to have these molecules randomly start bouncing left, right and centre off all of these atoms that are usually in our air, like oxygen or CO2, then we need for this to occur in a vacuum. And if we look back up at this, that's what I've drawn here. My handy vacuum. So this makes sure that all of this system is in a vacuum so that these ions can fly through it effectively. So there. Now let's think about the deflection bit. Let me just rub out this again, or I will run out of space and that won't be pleasant for anyone. Okay, the deflection bit. So we have a finely focused beam of ions travelling down this tube that I've drawn here. This is the direction that they're going. These are positive ions. Now, if we have magnets here and here, we can change the charge of these magnets so that we can alter the path of this ion. So it could go, if this magnet is too strongly negative, it will fly off and hit this wall, and that won't be good. If it's just right, the balance, then we can aim it down here and we'll get it into the detection chamber. Or if it's this one is way too negative, we'll just end up crashing into the side here. So if we have multiple ions in our sample with multiple masses, just like the tennis ball and the ping pong ball, it stands to reason that this finely focused ion beam composed of two different types of ions, so we have our two different ions that were in that solution X, when we change the magnetism on these two magnets, that these two different weight of ions are going to need a different charge to get through the gap. So whilst this may produce a charge too negative and that our green molecule will hit the side, the other one might find that just enough, our purple molecules might find it enough to go straight into the hole. And then we'd need to change that, and the beam would end up so that the purple molecules go in here and the green ones go in here. So by altering these magnets, we can effectively aim our separate beams of ions that would result from them having separate mass into different directions. So when we are able to change the direction of the ion beam, we can aim it into the detection chamber. Let's just go back up here and see what I was talking about. So here is where the ionisation happens. It's accelerated and then it is bent down into the detection chamber. And we would have several beams of ions going all in different directions because of the charge from the magnets. So then the detection chamber is where these ions are detected. If they just hit an empty wall, we wouldn't know that they were there in the first place, so what would be the point in having it? But no, what happens is our ions come into contact with a metal wire. This is my metal wire, and it is full of electrons because it has electricity built up within it, and that is what that is. So our ion comes in, and sorry, I scrolled a little there, ruined my arrow. Comes in hits our wire, and an electron jumps from the wire, let's just make this positive, jumps from the wire onto our positive ion to then, if you imagine this is what happens, to then make this neutral again. So it's just basically remade our original molecule. So when this happens, when this electron moves, these electrons in the wire flow for a tiny, tiny, tiny bit. And an electron flow is electricity. So when our molecule hits, we can measure a small bit of electricity. And obviously, the more molecules hitting will produce a stronger charge. So if we can change the intensity of those magnets, we will find that when the ion beams hit this wire at different times, we will get different charges that relate to the different strengths of the magnets that we used. So let me summarize. Back in our mass spectrometer, we can have a sample that's ionized, accelerated. Let's just make multiple molecules in this sample. Can be accelerated along, down the chamber. At this point, it's still just a single line with our multiple different ions in it, and then the strength of the magnet splits the ions based on their mass. So let's say the purple one is at the perfect thing to go first, the perfect mass to go first. So at a arbitrary strength of, let's say, 1, the purple beam of ions is detected. So we start hitting this and we can measure an electron flow on our computer. Here. So then we measure the voltage and we can assign that to the strength of the magnet. So then we change the magnet, because at the moment our other two streams of ions are too heavy and just end up hitting this wall. Like so. But then we change the strength of the magnet so that the next heaviest one, let's say it's the purple, no, we've already done the purple one, the yellow one, ends up hitting the detector. At this point, the purple one is too light, so it will start hitting this wall. And we can detect the yellow one, and then we can do the same for the green. So we can change the strength of these magnets, map the currents, and produce a graph. And the graph will look something like this. We'll have a y-axis and an x-axis, and on our y-axis we will have what is called the relative abundance. This is just a calculation to find where the most electricity was produced, so it will tell you how much of each of the compounds are in the sample. So it will give you, like, let's say in this drawing we had a lot of purple but only a little bit of yellow, then the purple will be really high on the x-axis and the yellow will be really low. And on the bottom we have a mass to charge ratio. This is called our MZ value. And this means that we can plot the mass of the ion relative to how much of an electric charge it produced. And that will give it the MR, so the relative molecular weight of the compound. So let's say we put chlorine through there and we ended up with two lines. We have one at 35 MZ, and this is going to be a really big line. It's going to hit about 75, and then we have one at 37, and this is a small line hitting about 25. What does this mean? Well, this means that out of our sample of chlorine, when we put it through there, something had a mass to charge ratio of 35 that was about 75% of the sample. And then another thing had a molecular weight of 37, which was its mass to charge ratio, that was only about 25% abundant. Now from the previous video, we know that chlorine has two isotopes, chlorine 35 and chlorine 37, and that the relative abundances are 75% and 25%. So this is what this graph shows. This shows us that in our sample we had two isotopes, chlorine 35 and chlorine 37, and that the relative abundances were 75% and 25%. Now you can imagine this usefulness if we apply it to something like if we got a sample of oil in there, we'd have a bunch of different chemicals in the oil, and we'd be able to see the masses of all of these chemicals and how abundant they are, so we can see what the primary element is. Now, this is about as simple as mass spectrometry gets. There are harder examples because of something that we'll call fragmentation, and we'll deal with that at a later date because that's a little bit more complicated. Thank you for watching.